I hope you are not too sad that this is the last exercise of chapter 13. But I also hope that you find this exercise to be enjoyable and enlightening. So, we are going to explore the scaling of eigenvectors. Now, as you are well aware, the scaling of eigenvectors is completely arbitrary, which is to say that an eigenvector of a matrix is going to be still an eigenvector of the matrix for any scalar multiple except for 0, obviously. And so, but that said, there are reasons to prefer certain magnitudes of eigenvectors, in particular for symmetric matrices, so that V transpose times V gives us the identity matrix. So what I mean by this is that there's an infinity of possibilities for how to scale eigenvectors, but some eigenvector scalings are better than others. And so with that in mind, what you are going to do in this exercise is to compute the norm of each eigenvector. And first you're going to confirm that the norm of each eigenvector is 1, and then you are going to multiply the eigenvectors matrix by any scalar you want. So you can multiply it by pi, or by 17, or by 47 quadrillion, 0.3, any random number you want. So the entire matrix V you multiply by some arbitrary number, or maybe you just want to pick a number at random. Just the important thing is that you're not multiplying each column by a different number, you multiply the entire matrix. So this is matrix scalar multiplication. Okay, and then, given that scaling factor, does that affect the accuracy of the reconstructed matrix and or the norms of the eigenvectors? Okay, so just to make sure this is really clear, we start off with some random numbers matrix, that is integers between minus and plus 14, compute its eigendecomposition or diagonalize that matrix, and then multiply this matrix V by some arbitrary scalar, and then compute its inverse. And then you want to multiply out these three matrices, V lambda, V inverse. Of course, you have to compute the inverse of the scaled eigenvectors matrix. And then the question is, does that screw up the reconstruction of A, or does this still accurately reconstruct A, even though you have arbitrarily scaled the eigenvectors matrix? Okay, and then, why does this happen, whatever the result is? And then you want to repeat exactly this, but use a symmetric matrix. And instead of using V inverse, you use V transpose. Of course, V transpose equals V inverse. So interesting question whether it matters. Okay, so now I will switch to Python. I'll show you my code solution, and we'll have a nice little discussion about this. So here I create the 4x4 random integers matrix between or containing numbers between minus 14 and plus 14. Here I take the eigen decomposition of the matrix. You can see this code is commented out. I'll get back to that in a moment. And again, of course, the eigen values that are output by NumPy just come in a list, but we need a matrix with the eigen values on the diagonal. Okay, and here I compute the inverse of matrix V, of the eigenvectors. Now, you've seen this several times before, so this is no surprise that these two matrices, so this product matrix and the original matrix, are the same, at least, within some reasonable rounding error. And so subtracting them should give us the zeros matrix. And then here I loop through all of the columns in the matrix, and then I compute the norm of that column, and I print it out. And A and V have the same shape, so it could be either one. Anyway, so here we see that the reconstructed matrix minus the original is all zeros. Now in this case, this ended up being a complex valued solution. So the matrix itself is only real valued, but the eigenvalues and eigenvectors, or at least some of them, were complex valued, and that you can see here. So I'm just dumping out the 4 eigenvalues of this matrix. You can see that they are all complex valued, and also interestingly, you can see that they come in complex conjugate pairs, which is something I also mentioned in the previous exercise that was about random numbers having eigenvalues in a complex circle, or a circle in the complex plane. So for example, you see here's the real part is the same as this real part. The magnitude of the imaginary parts are the same, but the signs are flipped. And same thing for this other pair here. Okay, but anyway, that was not the main point. The point is we can see that the reconstructed minus the original matrix is all zeros, so the reconstruction was accurate. And you can see that the eigenvectors all have unit norm. So here it's exactly 1. Here it's 0.9999997, really close to 1. We're going to let this slide here. Okay, so that doesn't address the exercise yet. We need to scale the V matrix, and that's what I do here. So now I say V equals itself times pi. So I am not changing any of the vectors, I'm not rotating any of the vectors. All I'm doing is scaling up everything in V by pi. And now when we run this code again, interestingly, we see that the reconstructed minus the original is still zeros. So we have a perfect reconstruction of this matrix, even though the norms of these eigenvectors is now pi instead of being 1. And why is this the case? Well, first of all, this is not surprising. You learned about this in chapter, I don't remember what number it was, but it was one of the first chapters about vector norms. If you scalar multiply a vector, you're going to scalar multiply the norm. So that's not surprising. What might be surprising, perhaps unexpected, is this, that we still get a perfect reconstruction. And the answer is here in the comments. So the scaling doesn't matter because the scaling is normalized out in the matrix inverse. So that is to say, here we're multiplying by pi, but effectively here we are dividing by pi. So it works itself out. So what this means is that the eigenvectors can have any arbitrary magnitude they want. We can still reconstruct the matrix perfectly if we are following this diagonalization formula. Now that said, some norms are better than others, and unit vectors are really great for lots and lots of reasons. Mainly that they avoid some computational issues. We don't have to worry about underflow or overflow. And also, unit length eigenvectors are only going to rotate and not scale another vector. Okay, so that was the first part of the demonstration. The next thing we want to do is repeat this for a symmetric matrix. Now, when the matrix is symmetric, which you see here, we don't have to explicitly invert the eigenvectors matrix. We can just compute its transpose, and that is the same as the explicit inverse. Now, you might not be surprised what's going to happen here. We are going to get some errors in the reconstructed matrix. And these are not tiny rounding errors. These are pretty significant errors. And the norms are the same. And why does this happen? Well, I think if you understood the concept up here, then I think you will understand why this happens here. And that's because we are not inverting pi. So we have pi in here multiple times. It actually ends up being in here squared, right? Because we are multiplying v times v transpose. So if we scale up by pi, then we're scaling up by pi again here. And then just as a final note, I'm going to explicitly invert this. So linalg.inv like this. And so now instead of computing the transpose or using the transpose, I'm going to use the inverse. And then you see that these are indeed the same. Now, normally, these should be identical to each other, right? The inverse of V should be equal to the transpose of V. But that is true only in the case where the eigenvectors are all unit norm. Otherwise, the V times V transpose, or V transpose times V, is going to be diagonal, but is not going to be the identity matrix. Anyway, I hope you enjoyed working through this exercise and found it illuminating.